put it on everywhere.
Okay.
Okay, good. Thank you very much for coming. So yeah, so I'm Peter Koroteev. I work at UC Berkeley and kind of well, mathematical physicist, well, transition into mathematician, something like that. Well, you'll see from my talk. Yeah. So I'll try to connect with the string theory and the string theory part of the audience and everybody else. So this is an attempt to make an introduction to this subject. So there's a project we've been working on with these people. So Anton Zeitlin, Edward Frankel. You can see he's in Cannes Festival apparently, and Daniel Sage. So Dan and Anton, they work at Louisiana State University, and Ed here is at Berkeley. And we have this series of papers in the last, well, 5 years or so, maybe 4, where we sort of gradually develop in this geometric approach to integrable systems. And well, in connection with, or rather inspired by some results in gauge theories and string theories, beta gauge correspondence, stuff like that. It's embedding into string theory. So, and it turns out that this name in the title, q-Oper, or just oper, plays a very important role, and it's you can use opers to understand like the landscape of all possible integrable systems and how they relate to each other. There'll be some dualities between them, and the how it all kind of sort of the how it allows us to understand the connection between other fields of mathematics and physics. So there's several motivation can go, several ways. So we have so there's a physics approach, math approach. So mathematicians have been studying quantum geometry, like quantum equivariant quantum K theory, quantum cohomology of spaces. And again, it's inspired by physics, by homological mirror symmetry, and then further developed to Giventhal's proof of homological mirror symmetry of Kontsevich-Witten formulae. And later, Andrei Okounkov he developed an approach how to do enumerative counts in sort of wider class of spaces, like the symplectic resolutions. And then myself and my collaborators, we sort of joined the project in kind of understanding in developing the connections between quantum geometry and quantum integrable systems. So physicists Nekrasov and Shatashvili, they found, well, some time ago, like more than 10 years ago, that there's an interesting correspondence between, well, it's kind of right now it has this catchy name BPS-CFT, right? So for the name to stand, it should have 3 letters slash 3 letters, right? So ADS-CFT, right? BPS-CFT. If it doesn't sound like this, it's not gonna stay. So it's a connection between some BPS count of well, some BPS states in certain quantum system, and well, some count of some states in conformal field theory, right? So, example, the AGT conjecture, which is now proven in most cases, right? The AGT correspondence is an example of that. So here you would look, for example, at BPS states in certain supersymmetric gauge theory with some number of supersymmetries, and match this count with the in that example, some integrable system that arises from the conformal field theory. Then sort of more formal aspect is the geometric Langlands duality, or in a sense you can Q everything. You can add a Q to pretty much every statement that you make. So it's like Q deformation. Well, you can also go to elliptics, but I'll comment about elliptic later. So what will be relevant to us is this Q-Langlands duality. And there's been some progress in physics and math as well. And in the end, if I'll have time, I want to mention this connection with what Vladimir Bazhanov is working on. I'm sorry, is Vladimir here? Okay, I don't see him in the list. Anyhow, so Vladimir and so Bazhanov, Lukyanov, and Zmolodchikov. So they studied the correspondence between, it's called ODEIM. Yeah, so two letters is also fine, right? The ODEIM, it relates certain monodromy properties of ordinary differential equations, right, with the spectrum of quantum integrable system. Yeah, so we'll talk about those. Are there any questions, general questions on the introduction, or so please, if you have any questions, just ask at any time, or you can write in chat. Also, I apologize, it's my Zoom number 4 today, so it's kind of okay. So one was in class lecture, but it's been long. It's been a long day. Okay, so let's get right into it. The what's a q-Oper? So think of pick a holomorphic vector bundle E over CP1, and consider this map, which I call M sub q, which just takes the local coordinate and multiplies it by a non-zero complex number q. And this is a q which will appear everywhere in the talk. So that induces the linear map of vector bundles. You can have E map between E and the pullback of E under this MQ, right? Which, if it sort of upon trivialization, it takes values in, well, GLN, right? So if it's some, if it's a, well, in this case, it will be SL2, but let's say for now it's GLN, and then the change of trivialization, the change of this coordinates, will as we change this linear map, right, the connection will be changed according to this sort of Q deformation of the ordinary gauge transformations, right? So if G is the group element, G of Z is like element in the loop group, right? Then A of Z becomes G of QZ, A of Z, G inverse of Z. And so if you like to get the familiar formula in the algebra, you do some Taylor expansion Q around 1, and you think of A is exponential to something, and then you'll get the formula with the two terms. So you can associate a difference equation, a difference operator to this operation. Basically, you can act on a section of the bundle. You can act with A, or you can write it as dq as a q shift of this section. So we define a meromorphic GLN, Q connection over P1 as a pair. So we have a bundle and the connection, and E and A, this kind of operation, where E is trivializable vector bundle of rank n over CP1, and A is the section of this sheaf, right? So it's basically sort of fancy way to say that we have this linear maps which are well defined in every trivialization. Such that A is invertible, so that's what GLN means. And then if you want SLN, we just require that the determinant is equal to 1. So this is the connection. Meromorphic if you allow certain singularities somewhere which do not accumulate. Now, what's an oper then? So here let me focus on just GL2 or SL2. So a GL2 oper on P1, it's a triple, right? So you have E, A, and L, right? So E is the vector bundle. So this is the connection, and L is a sub bundle. So because E is the rank 2 vector bundle, L is the line sub bundle of rank 1, and the oper condition reads as follows: we take the induced map from L to E mod LQ is an isomorphism. So you should think about it this way. So we take like this L is generated by some section, right? So you can do, and a section is just, it's a vector. It's a vector in two-dimensional space. And you can do two things with this vector. You can act on this with the matrix A, so it will rotate this and maybe stretch it, right? And you can do the Q shift, right? That's where this Q gradient comes in. And you require that these two vectors are linearly independent. So this is how this condition would look like. So you have so S wedge A of Z times S of QZ is not equal to 0. So later we'll allow this to be equal to 0 at certain singularities, but for now, let's say it's like that. Okay, and yeah, so let's add those singularities. Now, we can allow this inequality rather to fail at certain points on. So if you think of your CP1 as kind of, if you remove the origin 0 and infinity, it now looks like a C star, a cylinder, right? And this MQ action corresponds to kind of winding around the cylinder. So you can do the following. You can allow this determinant to vanish, well, at certain points. Let's call them Z1, Z sub M, where M goes say 1 through L, and also at a certain Q multiples of those ZM. So it's like you kind of form in like a tower of those points where this isomorphism fails. So these vectors are actually linearly dependent. So, and finally, there's another part of the construction, which is called Z-twisted oper. So what is this? It means that simply you can gauge transform it using these transformations, gauge transformations to a diagonal matrix, right? To element from the maximal torus. So if this was a bit too abstract, let's do an example, unless there are any questions on this slide. Okay, so yeah, so this is how okay. So let's write some explicit formula, and then maybe people will recognize some equations that they saw before. But before we do so, we need yet one more ingredient, which is called Miura SO2 q-Oper. So now we have not one subbundle but two. So they have L and L hat, where E, A, and L is the q-Oper which we defined on the previous page, and another subbundle L hat is preserved by the Q connection, right? So it's like an invariant subspace of that matrix in terms of linear algebra. So let's see how it plays out, right? So let's parameterize a section which spans L as with the two components, two functions, Q plus of Z and Q minus of Z. So this twist element is the diagonal matrix with the, say, eigenvalues zeta and zeta inverse. So we're thinking about a SL2 case. And this q-Oper condition is written like this. So it's a determinant of this 2 by 2 matrix. First column is Q plus Q minus, and second column is those functions shifted multiplied by Z, by the twist matrix. And if you compute the determinant, you'll get this equation, which is this quite often used QQ system in the theory of integrable systems. Some people call it Q system, but yeah, I think the more proper name is QQ system. And we can also get beta ansatz equations for the spin chain. Right, so we can take if Q's are polynomials, right? So remember, we live on CP1, right? So the gauge transformation, so it supports rational functions, right? So we have rational functions on CP1, and the gauge transformations should be rational functions. And we can have well, if we want section to be regular, so nowhere without any singularities, we can just say that Q plus is the polynomial, and these singularities are parameterized by another polynomial. And then so we can then substitute. So we can take this QQ system equation and then substitute instead of Z's. So Z is just the coordinate on CP1. We can plug in roots of polynomials Q plus, right? So because see here, so here there's a Q plus shifted. So if you substitute Z equals WK, this will not vanish, at least not necessarily, but the other term will. So you can do this, and then you do the overall shift of this equation, say by Q to the left, by Q to the inverse, and then you'll get another equation. And then you can divide one by the other, and you'll get this equation, which is the beta ansatz equation for the XXZ spin chain. So in other words, there's a correspondence between this Miura opers and the space of solutions of the QQ system and the space of solutions of the beta equations for XXZ. Well, you need to add some non-degeneracy conditions, but I'm gonna gloss over those. Any questions so far? Okay. So let's look at a bit more, in a bit more detail at the Q connection. So remember, I told you that there should be an invariant subspace, right? There's a subbundle which is preserved by the Q connection. So which means that A for Mura oper, the connection matrix has the upper triangular form, right? And then we want to find explicit gauge transformation, which diagonalizes A to the diagonal matrix with its eigenvalues. You can easily find this matrix. It looks like this. Yeah, so this way it happens that so you can formulate it this way, that the QQ system is the abstraction to diagonalizing the q-Oper matrix, the q-Oper connection. And remember what I mentioned to you in the beginning is that you can associate a difference equation to the oper. And whenever you hear a physicist talking about opers or q-Opers, he or she would typically write a difference or differential equation. So in this case, it's a second order difference equation of the sort. And then so the opers, the differential opers, I'm going to comment about them more later. So for differential opers, like regular opers, you'll have more or less a holomorphic Schrodinger operator, right? So it's a certain holomorphic Schrodinger operator with a potential with a certain prescribed behavior of certain prescribed singularities. There'll be some poles with simple poles and double poles, and then those simple poles and double poles they correspond to the singularities and multiplicities at those singularities. Yes, kind of. I'm explaining the geometric structure behind. Okay. Now let's see. So XXZ is a quantum integrable system. There's also a different type of integrable systems that arises from study of opers. And the one that is kind of connected to the q-Opers is the trigonometric Roisenars-Schneider, well, just Roisenars Hamiltonians. So consider, let's write again this non-degenerate SL2 q-Oper condition where polynomials q plus and q minus are of degree 1. In a sense, well, I'm not explaining it here, but it follows from the non-degeneracy, right? So if you want oper to be non-degenerate, all of those polynomials must be of degree 1. So if you shift it like this and then multiply by the twist matrix, you need to compute the determinant, and then you can sort of say it only has two singularities, right? So z plus and z minus, which is just some 2 points on CP1, and then we multiply it for convenience by this factor over here. Yeah, and then you get a quadratic polynomial on the left, quadratic polynomial on the right, and then turns out that the coefficient in front of z is the first Hamiltonian of this integrable system, and coefficient in front of, well, the constant term is the second Hamiltonian. Like this is like the, well, relativistic momentum, if you wish, the overall the total momentum. And oh, okay, it's more of this. Yeah, so never mind. So yeah, so this is the first Hamiltonian, this is the second Hamiltonian. And moreover, you can rewrite the determinant, as I'll show you later, as a spectral curve for this classical integrable system, where z will be the spectral parameter, and then well, we get the Lex matrix over here. So that there's yet another interpretation of the oper condition that it gives you spectral curve for some integrable system, which is the TRS, trigonometric Roisenars-Schneider model in this case. Any questions? Okay, let's keep going. Now, let's talk about those integrable systems in a bit more detail. So, of course, this oper story is not where they first appeared. There's the so-called Calogero-Moser space, which algebraically defined as follows: let V be an n-dimensional vector space over C, and then M prime will be the subset of this space GLV cross V dual, right? Which consists of this tuple of elements, matrices M and T and vectors U and V, such that this condition is satisfied. So on the left, we see it's like a quantum torus relation, well, some kind of version, it's like a Q commutator. And on the right, there's a matrix of rank 1, right? And then you subject this to the GLV action. So you can conjugate simultaneously both matrices and as well as those vectors. And if you take this kind of stack quotient, right, you get the Kaluza motor space, which is called M. Maybe some of you are familiar with the kind of more geometric approach. So this is, you need to look at the fundamental group of the torus with a puncture, right? And then the you have moduli, yes, we have moduli space of flat connections on this Riemann surface. So there's a puncture, and the sort of the holonomial around the puncture has only one distinct eigenvalue, right? It has Q, and yeah, basically the product must be equal to 1. So there's C, and then A and B are the sort of monodromies around A cycle and B cycle of the torus. And then, well, you can sort of do the following calculation. You can say, okay, let me pick a gauge where, say, one of the matrices is diagonal, say M is diagonal, and T will be whatever it's going to be from the solving the equation. And in that case, T will play exactly the lax, it will exactly become the lax matrix, which generates all the Hamiltonians of the system. So those traces, those Casimirs, they will become integrable Hamiltonians. Good. Moving on. So there is a family of quantum classical dualities. So I try to summarize, well, one of them here. So on the quantum side, we have, well, quantum spin chain, for example, this XXZ, SUN XXZ spin chain. And then, yeah, so like there's a whole dictionary, you can change the number of sites, you can change, well, various parameters. I'm just going to give you an example when it works kind of in the most direct way. So you have, say, n sites with a, yeah, and then it's SUN with n sites. So it's not coincidental that these n's are the same. In that case, like the representation theoretically, the problem is much easier, and you can do others for other numbers with certain work. But let me not talk about this. And then there are two types of deformations. One is called anisotropies. So we basically have two spins which are kind of near each other, and then two other spins can be farther apart from each other. So the strength of interaction differs, and you can sort of quantitatively describe that by introducing those anisotropies. And additionally, you can have a twisted boundary condition. So we have, open chain, you can close it with a twist. So there'll be some, matrix whose dimension is the, well, dimension of the representation, right? And then, well, it has some eigenvalues. Yeah, so those, let's call them those ZI. And then there's a Planck's constant, H bar. So right, and then so it's remarkable, yes. And then both here, you can there's this famous story by Hans Bethe, who would sort of develop this technique of diagonalizing the Hamiltonian of such systems, and sort of he did some transformations from, well, there's a smart way to choose the basis with some given number of fillings of excitation starting from the vacuum, right? And then you would add, say, 1 excitation, 2 excitation, 3 excitation, and you diagonalize it inside within each sector, right? And then there'll be certain equations, constraints, which, well, you need to solve for the spectrum to be found, right? And these are known as Bethe-Ansatz equations. So here's sigma is what is called a Bethe root, or it's related to the quasi-momentum of an excitation that propagates around the spin chain. So remarkably, those equations can be derived from a single function, kind of a potential or superpotential, if you think of kind of supersymmetric gauge theories. So there's a superpotential which is called Y, and in math literature it's called Yang function. Right. So it will be important on the next slide. So that's the quantum guy. And the classical guy is we have the well, in this example, there's a periodic. It could be periodic, it could be non-periodic system with particles, but they're not sort of staggered. They're not fixed at the points. Rather, they can move around. Right, so it's a dynamical system with certain. So yeah, all those particles, they interact with each other. So not only nearest neighbors, but every particle interacts with every other particle, as opposed to spin chain, where in this particular example we only consider the adjacent interaction between the adjacent sides. So the dual classical model to XXZ is called n-particle trigonometric RS model. So we saw the example for 2 particles, right? And this is how the Hamiltonians look like. So it's a certain. So P's are the relativistic momenta. You should think of them as exponents, right, of the kind of non-relativistic momenta. And in this case, the non-relativistic limit corresponds to taking speed of light to infinity, right? And that you would need to do some Taylor expansion of those exponents. So basically, the relativism in integrability means exponents, trigonometric functions, right? So there are rational systems, trigonometric and elliptic. And it will describe the phase space of this integrable system a bit more detail on the next slide. So basically, there's this homomorphic symplectic form, dp over p wedge dz over z, but all those Hamiltonians commute. And then upon this duality here, so the Planck's constant becomes the coupling constant in the classical model. Twist parameters, they are coordinates. The locations of those particles correspond to twist parameters. And the covariant parameters, which sort of describe the anisotropies, they correspond to, well, so at the energy levels of the eigenvalues of TRS Hamiltonians are elementary symmetric functions of those equivariant parameters. And in the end, so the energy equations and one-to-one, there's the correspondence between space of solutions of beta equations and this energy equation. So H bar in the rest of the talk will be denoted with Q. So Q and H bar is the same thing. So you should think of H bar as something that takes values in C star, like an exponent of something. Questions on this? Shall I go slower, faster, or what?
It was just a very naive question.
Yeah.
So can you comment more about choosing SUN for the n sides?
Yeah. So the right. So there's this. It corresponds to taking the n copies of the fundamental representation of SUN. So it's like, you know, in spin chain. So do you want like a math answer or like a spin chain answer?
Spin chain, well, maybe both. Okay,
so you know, in spin chain, right? So you have this. Yes, you have, you know, the. So you have, so you know, this beta and that's so the way it works, you have beta roots, right? Those excitations on several like level of nesting, right? So like there's like a fundamental, like the basic level, right? And then so where so it corresponds to fundamental representation. And then you can have, for example, you know, wedge squared of, you know, n, right? Then you go to the next level, and you can do the next one, and so on, right? All the way to the last one. So here I do not include these guys. I do not include these higher representations, right? So I have spins transforming only in the fundamental. Yeah. So right, but you could have more complicated excitations corresponding to this skew symmetric powers of the fundamental. So they are not here. You could include them. It will change something on the other side, and well, essentially, if you pick other guys, you would need to introduce some degeneracies. Like some of those coordinates will go away. Does it answer the question or not? Right?
My was even more naive. I was just considering whether you can deform this by considering an n-site SU3, for example, X.
Yes. I can do that. I can do that, right? So
okay.
if say if this number is bigger than that number, then well, like essentially the phase space of the classical system would kind of chop into some disjoint unions which do not talk to each other. Like it will kind of, the system would split. So you can, yeah, so think of this way. So there's this beta equations, you can impose some degeneracy conditions so that, you know, there will be some cancellations of those polynomials, and then you lose degrees of freedom one by one. So in a sense, this is kind of the maximal system where kind of all degrees of freedom are generic.
Okay, this answer, thanks.
Yeah, that's right. And yes, like it also corresponds to having this, the most non-degenerate oper, kind of what was in the first part of the talk. Yeah. Other questions? Right. So the QQ systems. So yeah. So the beta equations and one-to-one correspondence with the QQ systems, and this integrable classical models will be related to q-Opers. So here's sort of more formal description of this duality, which is sort of purely geometric. So let's take let's M is the Collider motor space, and M Schrick is it's another Collider motor space, but it's dual in the sense that well, in the first one you want you know, your twist variables to be coordinates, and the other one you want the anisotropy parameters to be coordinates. So it turns out that you can do that. So there is something which is called, well, bispectral duality, or in physics it comes from three-dimensional mirror symmetry, that in trigonometric case there are two independent descriptions of the same integrable system. So you can consider this well, 4n complex dimensional space, right, where if n is the number of particles, you take this symplectic form, which is basically the difference of symplectic form on one and symplectic form on the other, right? And then you can consider two Lagrangian subvarieties, right? So you know, Lagrangian subvariety is a half-dimensional subspace, right, where the symplectic form vanishes, right? And then there'll be two types of Lagrangians. So one corresponding to kind of well, when it's denoted here with mu. So it's one type of variables vanishing, and in the other sort of the other types of variable, the other type of excuse me, symplectic form vanishes in both. It's just the so this L tau is from SA M Schrick, and L mu is from M. But like you can also look at the product. Now in generic position, so these are, so they will intersect transversely, right? So there'll be just, you know, transversal intersections, and at those intersections, this potential, which gives beta equations. Oh yeah, I forgot to say, right. So before we go to potential, right? So how do we define this momenta, right? So it's also part of the dictionary with quantum classical duality. So it's if you have the right. So we have the, well, like in canonical transformations. So there's a generating function, like a canonical transformation of type 1. So you have a coordinate, and then the momenta is the derivative. In this case, it's an exponential of the derivative, because we kind of work in trigonometric sense, but it's the derivative of this generating function of the canonical transformation, right? And there are two types of those. And then the in a sense, this y, right? It generates the Lagrangian submanifold. So right, so we have two types of Lagrangians. They intersect, and in those intersections, these generating functions are the same. They match, and you can show that this corresponds to the solutions of the beta equations, to those beta roots. So there are two descriptions of the same integrable systems as system at once. You have determinant. Well, you have so one spectral curve for TRS model in one frame, another spectral curve for TRS model in the mirror frame, right? And sort of what happens here is that to specify L mu, So L mu is specified when eigenvalues of M are fixed, and then this sort of you impose what is called the Slodaway form on matrix T. And the Slodaway form is basically it's the matrix T looks like, well, a bunch of blocks, like Jordan blocks, but only like those blocks have a form, each block has the form highest weight element under that joint action plus plus E, where E is the raising operator. So there's we don't have to go into this, but basically there's a certain kind of block structure for the T matrix. And then when we specify the Lagrangian in the other one, so we fix eigenvalues of T of the other matrix, and we impose Slodaway conditions on M. And then sort of solutions of beta equations correspond to intersection points of these two Lagrangians. Yeah. Now, for string theorists in the room, we can all think of this in terms of brains. So let's go to type 2B, like this vanilla Hanani-Witten approach. So we have NS5 brains, we have D5 brains, and then there are D3 brains that stretch between themselves, right? Between each other. So, right. And then there are two ways we can understand this picture. One is drawn here, when sort of all the NS5 brains are on the left, all the D5 brains are on the right. And then, so D3 brains, so infinite D3 brains, they support n equals 4 Young mills, right? The stack of D3 brains supports n equals 4 Young mills. If you make them finite along one of the directions, which is this one, you will break supersymmetry in half. So you impose BPS boundary conditions on the left and compatible BPS boundary conditions on the right. And turns out that, well, the choice of the boundary conditions is exactly like in one-to-one correspondence with choice of these two Lagrangian submanifold. So you will have what is it, moduli space of n equals 2 star theory on a segment, right? And also compactified in a circle. And yeah, so in the presence of certain BPS boundary conditions on the left and on the right of that segment. Right, so that's the classical story that gives this TRS integrable system, and the quantum story goes as follows: you need to take those brains, D5 brains, and move them inside, and now you have a picture like this, right? Some number of maybe I should use different color. Let's use black for NS5s, and then we'll have D3 somewhere here, right, and then D5s will be there. Right, and now it's a three-dimensional theory, which gives you a three-dimensional quiver description. And Nekrasov-Shatashvili dual of that would be this spin chain, would be the quantum spin chain. So of course, in a sense, string theory gives you basically this duality on the nose if you just look at the brain picture from the right perspective. Okay. Yes, question?
Yeah, I'm sorry, I'm a bit sleepy. Could you remind me, so you're on the Coulomb branch for this theories, right?
I'm on what? What are the theories?
The Coulomb branch of this theories.
Oh yeah. So Coulomb branch, right. So yeah, that's right. So you run the Coulomb branch, yes.
So the Coulomb branch waves, they corresponds to which parameter in your spin chain and the masses of the.
Yeah, good. Thank you. So in two-star theory, right, so you have this n equals 2 star, right? So the mass of the hypermultiplet, right, essentially exponential to the mass is equal to q. Right, or h,
right?
Yeah, sorry. What happened? Yeah, so it's adjoint mass or h bar on the previous slide, and then the kind of positions of this points where they meet with the brains. So these ones, one of them are, well, sort of the twist anisotropies, right? And the other guys are the twists, yeah, or the other way around. Yes.
Okay. Okay, thanks.
Yeah, so everything, you know, in string theory, everything is geometric, and this is the case here, yeah, which is really remarkable. So in a sense, kind of, so yeah, I was working first on this. Yeah, so we did this with David Gayotta when I was a postdoc at the Perimeter Institute, and so we had this paper. We were very excited, but then kind of it was not clear how to grow further, kind of into kind of generate some more mathematical results. And in a sense, that's where this study of q-Opers came from. So I talked to some mathematicians, and then we sort of started to develop this this approach. So in a sense, now we think that opers are in a sense more fundamental than all this, right? Because in a sense, this is only a certain type of opers, like in the presence of some specific non-degeneracy conditions. Right. Okay, so I mentioned that there is a more than one, there's more than one theory, more than one kind of type of oper. So it turns out that you can draw this kind of diamond. So if you do not include elliptic models, then there's a diamond with the, basically there's a hierarchy in periodicity in momenta and in coordinates. You can have C star cross C star, you can have C star cross C, C cross C star, and C cross C. And then in every corner, we'll have different, we'll have two integrables. You'll have its own type of oper, and also its own type of integrable system, or rather two integrable systems. One is classical, one is quantum. So on top of the hierarchy, we have q-Opers on C star, and that gives you a TRS model and XXZ model, and they're related to in the way that I described in previous two slides. And then you can take various limits. Then you can, so first of all, you can so think of kind of the, well, instead of C star, you can think of CP1. And then you can also study q-Opers on CP1. I'll give you an example of that later. And instead of TRS model, you get the trigonometric Calogero system. And this spin chain will be more familiar, Heisenberg XXX magnet. Or you can sort of do the other limit. You can take, instead of q-Opers, you consider just the normal opers, like Beilinson and Drinfeld did. And there are two choices. You can do them on C star, or you can do them on the projective line. Because you need the why we're choosing this is because we need the action of the group, right? So for example, P1 supports addition and multiplication, right? So C star supports multiplication. So basically, we're only limited to basically three choices, right? P1, C star, and the elliptic curve. So we're working right now on the elliptic curve. It gives a very interesting model, which is called DEL, double elliptic integrable system. Sort of the joke goes that DEL is not a computer, right? So because nobody is using DEL computers anymore. Well, almost nobody. Right. So yeah, so it's a very rich story. Questions? Okay, so let's look at the.
So you have elliptic opers for the DEL on an elliptic curve. That's
Yeah. So it's actually right. So it will be like you have a, the diamond will be 3 by 3, right? It will be well, you see, like there'll be 5 more points, right? And then, well, like this, right? So there'll be a bigger diamond. So DEL will be on the very top over here.
Yeah. And so you have precise expression for these opers. For this
not yet, but we have some idea. Yeah, so it's coming. Yeah. So essentially, the treatment should be universal to like essentially the rule is the same. So if you go sort of in this diagonal, you have g-Opers on P1, C star, and then it will be elliptic curve, right? If you live on this diagonal, it's difference opers, q-Opers on P1, C star, and elliptic curve. And the next one should be elliptic opers, which do not exist yet, but they should be.
So to go to q-Opers, you go from differential to q-difference operators. To go
Yes.
to the elliptic version, what kind of operator would you consider?
Well, I mean, so it's a formal operator. So you have a theta function whose argument is a like shift operator, right? So P is like e to the d over dx.
I see. So you have like some kind of infinite product.
Yeah. So that's right. Yeah, it's a formal operation, but you can define it. Like you can even talk about convergences and stuff. Yeah. So del Hamiltonians, they exist. So I have a paper with Shamil Shakirov.
Yeah.
Yeah. So we have explicit formulae for quantum del Hamiltonian. So it's double elliptic. It's elliptic both in momenta and in coordinates. Like the kind of Hamiltonians written as some high genus theta functions. It depends on, well, a bunch of parameters and some other bunch of parameters. Yeah, and it doesn't split into product of simple theta functions.
Or higher genus theta function.
Higher genus theta functions. Yeah.
So what's the genus related to?
Number of particles. It's
Okay.
I think genus is equal to n plus 1.
I see.
Okay, so I have like 15 minutes. Is that right, Jock? We started like 5 minutes later.
Yeah, I think it's right, Peter.
Okay. So right. Well, I need to cut some corners, but yeah, I have like you guys can look at my slides later. So I'm not going to be able to cover everything. So I just want to maybe highlight some important points. So let's do the SLN example. So the for the q-Opers, so how do we define an SLN oper? So now we need to take a flag of sub bundles, right? So we have L1 inside L2 inside L3, etc. inside E, and then we require n-1 isomorphism, right? So at every location, so Li factor Li-1 to Li plus 1 Q mod Li Q is an isomorphism. So we write this oper condition every time. And they all can be written in terms of this quantum Wronskians like determinants. So you take basically section S, right? You multiply by Z, you shift it, multiply by Z to some other power, and so on and so forth. So there is some kind of shifted structure here. And in the end of the day, you come up with some determinant which looks like a Wronskian, sort of finite difference Wronskian with those twists involved. Right, and you can think of kind of the structure reminds you, well, diagram of a quiver. In fact, it's quiver gauge theory if you want. Yeah, so this beta equations compute the space of ground states of the quiver gauge theory. So mathematically, you compute in equivalent quantum K theory of this quiver variety. But yeah, so oper provides you yet another sort of viewpoint on that. And then, so interestingly, so what you can show, and I can comment on it later, so that the components of this vector of the section S, so we saw it in example 2 by 2, right? So we had Q plus and Q minus, and turns out that in the n by n case, the column vector, which parameterizes the section, so say of L1, the first one, the line bundle in this flag, all those components are some Q functions, right? So the first two are Q plus and Q minus, and you can ask what are the other Qs? Well, the other Qs turns out to be what is called Berkeley transformed Qs. There's notion of, well, mutation, like cluster like algebra. There's a cluster algebra structure on this oper, and you can do the mutations. You can basically do some cluster like transformations, which would take one polynomial, map it to the other polynomial, and you can make them as many as rank of your group minus 1. Rank of those. Okay, rank of the algebra. Yes, so, and then so you can do this. So well, let's just do it. Let's do it example. Let's do an example for TCM, right? So, and I hope you'll appreciate the connection with other stuff. So I remind you, TCM lives in this corner. How do I remove annotation? I need to quit and open it again, right? So TCM lives here. So these are q-Opers on CP1. So we expect additive shifts, not multiplication by q, but some additive shifts. And you can write this Wronskian. It will look like this. We have, S, and then S shifted by epsilon, where epsilon is like the logarithm of q, multiplied by Z, and so on. and all the way to the j minus 1, right? And then you can show that all those q polynomials that satisfy the QQ relations. So there will be r minus 1, where r is the rank, right? You can write them as the ratio of this determinant of such a Wronskian divided by the determinant of the van der Monde matrix. And the van der Monde matrix is formed out of those twists. And remarkably, with this presentation, the QQ system is equivalent to the so-called, Alice in Wonderland identity, right? It's the Desnanot, Jacobi, Lewis Carroll identity, which works as follows. So you can take square matrix, compute its determinant, and you can do various things. You can remove a row and a column, right? So say first and the first one. Then you can do second and the last, and then you do it in a different order. So it turns out that this kind of combination of determinants with columns and rows removed is an identity, right? And this is on the nose reproduces the QQ system. Okay. So yeah, and then let's see how to get the lax matrix from here. So right, so we write down this equation, and then so that was Gabriele was asking about the structure. She asked spin chain. Why do I have SUN with n sides, and it's a fundamental of SUN? So here I take the same kind of idea. So I only have the singularities that appear only on the in one of the equations, either on the first one or on the last one, depending on how you count, right? So in a spin chain language, I'm only considering fundamental reps. So there's just some n copies of those fundamental representations, which means that I have only singularities at the last node. Well, and then I can turns out that the following thing is true, is that if you denote this one lambda as p, it's a polynomial of degree n with some roots, right? Then the non-degenerate condition for this SLN plus 1 oper polynomials which describe the section of degree 1. And then turns out that you can rewrite the QQ relation, all those Wronskians, as the spectral curve of the TCM system. So here M is lax matrix, right? So determinant is this is the spectral curve is equal to P of Z, and the calculation is straightforward. You simply write down this matrix M as Z plus something, and then this something looks like the Wronskian matrix, right? So Z multiplied by the Wronskian part plus some at the tail. So you can divide by the Wronskian determinant and then write as ratio of determinants as determinant of the one matrix times the inverse of the other. And that's how you get Z plus some other matrix. So this way, the lax matrix is the product of this Q polynomial evaluated at 0, right? Times the inverse, like this Q matrix, the matrix M at 0, which then whose determinant is given by the Q polynomial, but it's a matrix multiplied by the inverse of the Wronskian matrix, well, on the right, and this is the lax matrix. Yeah, and then you can write it explicitly in these are the diagonal components, momenta, and this is the potential, right? And the off-diagonal components that look like this. So you should think of the zeta psi as exponential to some x. So this is in fact is sine or sinh, depending on the reality conditions, sine x I minus xk. Yeah, so trigonometric calogera has potential 1 over sine. Okay. Good. Okay, so let's keep that. I don't have time. Now, the question?
Yeah, sorry, a quick question. I'm trying to understand a bit this connection between q-Opers and QQ system.
Yeah.
You're saying that if you start from a q-Oper, you can derive a QQ system?
Yes. So the q-Oper condition, is equivalent to the QQ system. Yeah. So
it's equivalent. So the other way around, right? If you start from a QQ system, you can write q-Opers.
No, you can do the same. You can do the same. So, because the formula tells you how. So essentially, right. So so you say you start with a QQ system, and then you ask yourself, how do you just? So it's a functional equation, right?
Yeah.
And if you think of it abstractly, right? So just as an equation, so turns out that the following is true. So if you write this matrix, right? This Wronskian, And turns out that yes, there's one for Q plus, there's another one for Q minus where you skip one of the rows. And yeah, you can just check that they satisfy the equality, right? And then you can interpret this as a this kind of thing, which is the definition of the q-Oper.
I see.
So basically, it tells you that there's a flag of subbundles, and there's this isomorphism on every in every arrow.
But you're always starting with polynomials. You could start with theta function for elliptic.
In principle, yes. But then, well, you know, the geometry will be more complicated, right? So you have to, well, describe those theta functions and stuff. Yeah. So it could be done. Yeah. I don't see any problems. Yeah.
I see. So,
well,
so
other
for
than
them, you could write some kind of QQ system for them, for instance.
Yeah, we hope so. In fact, it's an open question. So what will be the spin system corresponding to del, right? So, so here TRS gets XXZ, RCM, rational calogera, gives rational Gadan model, and well, these guys, and the question is what corresponds to del, right? So del goes to what? I don't know the answer. There's also XYZ chain, you know, by Baxter, right? But it's not. Well, I don't know where to put it. Either here in the top of the hierarchy, or maybe it will be in one of those corners, which is one level down. I'm not sure.
Okay. Okay, I see.
Okay.
Thanks.
Good. So, right. So maybe I can have like 5 minutes or so. Let me do the what. So you can define oper not only for SLN, but for, in fact, for any simply connected complex Lie group. And well, you need to, the construction is a bit more abstract. You need to work with this double Brouillard cells, some Zariski open then subsets inside your inside of your base, but all in all, it can be done, right? You can similarly define the the Q connection, the Miura oper, right? So the oper condition would look like this, right? So it's like you need to specify that this map from, you know, there's a principal bundle of a P1, and then so this A, well, defined in some Zariski open subset union intersection with inverse of that under MQ, right? Takes values in this double Brouillard cell where C is a Coxeter element, right? You take the product of all reflections in the Weil group in some order, right? So that's kind of interesting part of this, so that our result does not depend on the type of the root system. A, D, E, and that even doesn't have to be simplaced. You can do C, B, you know, F, right? So, you simply need to work with this Weil reflections. So the connection will look like a certain ordered product of reflections in the Weil group multiplied by some functions that takes values in which depend on Z on the loop variable. The power of those Cartan. So alpha check is the Cartan, right? And then n's they live in the unipotent radical. Basically, you can write a formula for the oper, which would look like, yeah, let me skip that. Well, you can add singularities, you can do the twist and everything. But basically, yes, just think of your, so say you have a Dynkin diagram for G. Let's take what is this? Is E6, right? And then you can start maybe from one vertex of the one node of the Dynkin diagram, go to the next and go to the next in some order, right? So which would kind of allow you to interpolate between different roots. And it's done in the following way. So first you pick one, right? And then you take the irreducible representation of G with highest vector omega I, say, which is stable under the positive Borel, right? You take the highest weight vector and you act with the lower end generator Fi times V. And these two guys, they form a two-dimensional subspace, right? So by construction, it's invariant under B plus, under the Borel subgroup, right? And you can construct an SL2 q-Oper for this two-dimensional subspace, which we already know how to do. it's called Muir-Plucker oper, because it's inspired by Plucker embedding Plucker relations in algebraic geometry. And then you can, so each of these Plucker opers a sub I for every node in the Dirichlet diagram would correspond to 2x2 matrix like this. So instead, so it's more complicated because the instance, right? So if you say sit on this middle node, right? So if this is your node I, then it talks to 3 other nodes, right? And then basically because your oper knows, like you pick certain order of reflections in the while group, then so this node will talk to these 3. So AGI here is the Cartan matrix, right? And then you can write this Muir-Plucker q-Oper for every node. For every node, you'll get its QQ system, which now look like this. Again, there's some right-hand side is more complicated. And the most complicated part is to kind of stitch everything together, sort of to show that the bona fide oper for group G, GQ oper, is actually equivalent to this Plucker construction, right? And this is done by, this quantum Berkeley transformations. And I mentioned them before when we talked about the components of the section, but basically, if you have a QQ system with some Q pluses and Q minuses, you can do this change, right? There's a, so on the level of the QQ system, you replace on the ith node Q plus with Q minus, and some other things with a twist. And in terms of the oper, what you do, you take the Q connection and you twist it. So let's say this oper was in B plus, like for SLN, it's an upper triangular matrix, and you twist it with something from B minus, right? So Fi is the lower in, is the negative root. So if effectively what you're doing, you're changing the orientation of the Borel, you're picking a different Borel subgroup in G, right? So choice of your B plus in G is up to you, right? So it's just convenient, say for SLN, we said all upper triangular matrices, they live in B plus, but we don't have to do that. And there are handful choices. There's the n factorial choices for permutation group and whatever the number of elements in the while group of for the other root systems. So you can, by successively applying those Berkeley transformations, you can basically show that these 2 constructions are the same. So you can kind of, by traveling around the Dirichlet diagram of your system, of the root system, you can kind of uncover, you can describe the whole oper here. And there's a theorem that every z-twisted Muir-Plucker oper is also just a z-twisted Muir oper. So in a sense, you can remove Plucker. So it was part of the auxiliary construction. Yeah, and it opens very powerful, sort of interesting directions. For example, you can talk about the generalized Wronskians. So we think of Wronskian as a determinant of this matrix, right? When you have this derivatives and stuff, or the finite shifts. But now you can define it abstractly for any group G. It's using so-called principal and generalized minors, right? And then so basically you can show that basically these minors are, so if V is the diagonalizing element of your q-Oper, like, or V inverse, it's the thing that maps A of Z to V of QZ times big Z times V of Z inverse, right? Then the Q polynomials, Q functions, right? They're related to the generalized minors. Like, so I wrote the formula for SLN, but you can make sense of it, of the analogous formula for any group. Yeah, and there's an analog of Lewis Carroll identity for type A, right? So for type A, there's a relation which on those determinants, which in type A reduces to the Lewis Carroll identity. Right. So I think I'm out of time. So I have several slides about the BLZ, but yeah. So if you give me like 3 minutes, I can do that. If not, then I can stop here.
Maybe we can ask if there are questions at this moment. If not, probably you can comment on this.
Yeah, so I can talk. Yeah, any questions about general type about any group G? G-Opers for any group G. I'm just looking if so Vladimir Bazhanov is not here. Okay, so I hope I can meet him at in Canberra. Yeah. Okay, so yeah, maybe question comes to just sort of this brings us to a new result, which is sort of conceptually interesting, which can only be realized when you know what q-Oper is, right? So but first I'm going to remind you what BLZ did. So Bazhanov, Lukyanov, and Zamolodchikov, and then there's the mathematical papers by these authors. So it starts from very simple, well, a very familiar problem to, well, pretty much every credit student in theoretical physics. You start off with a Schrodinger equation in a centrifugal potential with, and the potential looks like 1 over x squared times x to the 2m, right? So for now, assume that m is integer, but later we can remove that that constraint. So you can write it as in the vector form, right? So if there's a column vector psi1 and psi2, right, and then you can write it as the two ODEs, a system of two coupled ODEs, which has a interesting geometric structure. It's called affine SL2 oper, not q-Oper, but oper, because connection looks like the derivative, right, plus, well, this thing. So here E is the positive root, and F, well, should be actually written not F, but E0 is the affine root. So it looks like this. It's like, well, del x plus L of x minus L of x, 1, and here it's P of xb. Right, so this is the connection, and the equation has interesting symmetries. So BLZ called them lambda and omega. So lambda just flips the L to L minus L minus 1. So just symmetry of this term alone. And omega does something interesting. So it does the Q shift of x in which the question is written. And also, if you shift x, excuse me, if you shift x, because of this function here, to make everything homogeneous, transform homogeneously, you also need to shift. You also need to shift E, right? To make it I think it's 2m here. There's a typo. 2m, right? And you don't do anything with the L. So in the oper language, this transformation omega is realized as the rotation of the loop of the Katz-Moody variable t, right? So affine the algebra has this Katz-Moody parameter at t, which you can shift. You can multiply it by something, and this is what we're going to explore here. So the sort of what BLZ said that, okay, we can look at asymptotics at infinity, which looks like this, and we can look at asymptotics at 0 that look like that. And let's see what happens when we act with those symmetries, omega and lambda, on those solutions. So let's call one chi plus is the one over here, and chi minus is the one if you act on this with omega. And the same we can do with the size, right? So solutions around 0 and solutions around infinity, right? And then the kind of the observations comes in the following way, that you want to expand solutions around 0 in the basis of solutions around infinity, and see what the expansion coefficients are. So as BLZ showed, and then also Dory and Tatel and Dory, what's the DDT, right? So Dory, who is the third guy? Okay, so he'll come to me, right? So you can show that the psi minus is equal to, yeah. So right, so you get psi minus equal to well, some d chi minus plus d with other coefficients chi plus, and those d's are spectral determinants of the Schrodinger equation. So if e's are the energy levels, let's look at en, right? If e's are energy levels, then turns out that the coefficients of the expansion of asymptotics around the origin in the basis of asymptotics around infinity of those fundamental solutions are those spectral determinants, right? And then it's interesting here that the omega acts on chi in a triangular form. And we know what triangular form is, right? It's a q-Oper. So there's something here, something here, something there. So if you look at these two equations, so in the basis chi plus chi minus, this operation is triangular. And that's exactly what we've seen before with the q-Oper. So so the ODEIM itself says that in these terms it can be formulated the following: is that the Wronskian of size by its solutions around 0 is equal to this thing, and then essentially the statement is that the q functions q plus and q minus are those spectral determinants. That's kind of the fast way to formulate what ODEIM is. What we're saying with the Frankel and Zeitlin is that there's a connection between affine opers for G, well, on the disk, and q-Opers on CP1 on the projective line. And the reason is because what I explained here. So there's like there's a monodromy. Well, I don't have time to talk about the formula, but basically you can think of a q-Oper as the monodromy of the differential equation, right? So there's a q monodromy that gives you the so that's two statements. One is that this monodromy of the solution. So when you multiply x by 2 pi I, so that gives you the it's given by the twist in the q-Oper. And the second equation is that this q shift, or like this wall crossing transformation between different Stokes sectors of the ODE, is given by the product of q-Opers, right? So if m is integer, there are m plus 1 elements here, and if m is not integer, is a bit more complicated. But this is story for another time. So basically, the upshot from this part of the story is that there's a connection between affine opers and q-Opers. You can kind of think about it this way: there's a circle action in both cases, which is realized differently, right? It's realized as Kac-Moody, in this Kac-Moody sense on the left, and it's realized as this MQ, right? This Q action on the right, and in some sense they're equivalent. Okay, thank you very much, guys. Yeah, so that's all I wanted to say.
Thank you, Peter. Is there any more quick questions?
Yeah, so I have asked already many questions, but may I ask another one?
Yeah.
Right. So you mentioned a bit earlier that you can start from an Lie algebra and this kind of Miura decomposition where you associate 2x2 oper to each node of the Dynkin diagram. So can you do also this for an affine Dynkin diagram? You get some kind of toroidal oper in this way? So
it's a good question. Yeah. So we haven't done that. I hope it would be interesting to see. So although we have a different notion of a toroidal oper where we take just, it since what we call toroidal oper is the, okay, so I know how to get toroidal oper differently. So yeah, what I'm saying, I agree that in principle it should work. In fact, it's a nice thing to try, right? Basically saying that you have, an, like, a and hat, right? And then you would see what happens if you go around and come back, right?
Yeah.
Right. Yeah. So that's right. So we could realize toroidal oper. So we have Anton and I have a paper which is called toroidal q-Opers, and we do the following: we take a infinity Dynkin diagram, right? So a infinity, and then you impose some periodic boundary conditions, right? So you first start with this, the truncation of this infinite Dynkin diagram. You can realize it using this quivers with framing. So I think that comes back to Gabriela's question about SUN. So if you take this quiver with like n minus 1, n minus 2, and 1, so that corresponds in the sense that I've been describing to the SUN spin chain on n sides, right? With the n copies of the fundamental representation. So this beta, right? And then you can send n to infinity, right? So you can either do this one, or you can kind of have a different framings, because you want framing, right? So you actually want to have some framing here. Well, otherwise it's just too singular of a space. So imagine you impose periodic boundary conditions on every node. So then it will close to this quiver, right? Which is the Giese-Kernel-Kajima, or like ADHM in physics language, right? So so you can do that, right? So then to get frame in here, there's also a way to make a frame in here. So right, so yeah, so thanks for the suggestion. It's an interesting question. Yeah. So and we can see if what you are saying will give us the same stuff as here.
Well, yeah, naively you would get higher toroidal, a higher rank, because the ADHM case, the toroidal GL1 is kind of
but you can, right? So but you can do others, right? So if you kind of close it like this, you'll get more, right? You'll get so we have all of them. So we have this GL and hat. So like a quantum toroidal for any GLN. So the nice thing about ADHM, because it's self-mirror, right? But this one is not, but it's also a circular, like necklace type quiver.
Yes, and you have QQ system also associated to that.
Yes. So just the paper is called. That's where it's here. Toroidal q-Opers, 2020.
I see. I might have missed this one. Okay, thank you very much.
Yes, it's in JUICEO, published.
Okay, I think we can probably.
Oh, dining, Koroteev. Thank you, Gabriel. Yes,
it's okay.
Because it's already 11 p.m. in California.
Yeah, I think you should go to sleep, but hopefully you will be here in Australia in a few weeks, and probably Jean-Emile should come to UQ or go to ANU to talk with you as well.
You're coming to Australia?
Yeah. So like I'm applying. So the way Australian visas now work, you just it's attached to your passport, so you don't need to go to the consulate. And I thought, well, I just apply and I can fly in. But like it's been almost 3 weeks, and I'm still optimistic. But so they say 90% of the cases are processed within 25 days, and there's still several days before that.
Yeah, you shouldn't really trust this. I mean, my visa was supposed to be processed in like 3 or 5 months. At some point, it took 2 years.
What? But you had immigration visa, right?
No, I think you should be fine. So how long will you be staying? Where are you going?
Maybe. So I have a cutoff. I organize a program at Stony Brook in end of August, like 28th. I can stay several days more. So hopefully you'll end